In this video, we're going to go ahead and go over section 3.5, exponential and logarithmic models. This is part of unit 3, exponential and logarithmic functions. Okay. Basically, they're just word problems that are based on either growth or decay. And to do those kind of word problems, we use the following different types of models. Okay, so go ahead and just copy all these. You have our exponential growth, which is by this equation right here. Exponential decay, which is basically the same. We just change our b to a negative. It's going down. Okay. Something called the Gaussian model, which we're going to see a little bit later, actually, when we get to matrices. And we also have two more, logistic growth and logarithmic models. Don't let the model freak you out. It's not that bad. Okay. We're going to go ahead and do 4 examples based on some of these models. Before we do that, just really quickly, here are the basic graphs. I'll go ahead and scroll down to the next ones in just a bit. So we have our growth that goes up, decay that goes down. Notice they both go through the number 1. The Gaussian model has a kind of like a weird little hill looking curve here. And then we have these ones down here as well, which is the logistic growth, kind of looks like an S, okay? Natural logarithm, which we have seen before, and the common logarithm, which looks really similar to this one. It's just slightly a little bit, not as steep as the natural log. Okay, and those are going to be the 6 models that we're going to base our examples on. Okay, so let's go ahead and start right with an example. We do have some data here. These are from your textbook, just to kind of give you a heads up. I'm not going to write the entire word problem. I'm kind of paraphrasing. So if you wanted to get a better view, you're welcome to go ahead and look at the text and see all the details for the problem. Okay, but I'm just giving you the main stuff here. We have this exponential growth model. S equals all of this, okay, between 10 and 14, where S is the billions of dollars spent in the US on advertising and T is the year. So we're going to pretend that T equals 10 is the year 2010. Here we have a table that represents data that was actually collected. In other words, this data right here, and I'm going to kind of color code it a little bit. This data right here is not based on the model. This is data that was actually collected, using statistics or some sort of survey or something. The exponential model is what I'm going to show you with this equation here. So give me just a bit so I can go ahead and get that on a calculator. All right, so here is what I got when I graphed this, and I went ahead and used y and x instead of the letters there, obviously. I want to make sure everything is the same. Remember that for the E, you have to actually write the letter E. You click on the ABC and it'll give you all the letters, the alphabets. All right, so we want to find values for this exponential model, okay? Basically 2010 through 14, I'm going to find the actual value according to the model. Okay, so I guess it wouldn't be the actual value, it'd be the exponential model values. To do that, because I know some of us have had some issues with this, you want to go ahead and get the table. So we can either do it by plugging the numbers straight into here, or we can just get a table by clicking on the little gear here and then clicking on the table. You're going to see that we have this table here, and it does not have the values that we want. So we're going to go ahead and make those values. So let's start with 10 because that is the first one that we want. So let me go ahead and type them in really quickly. Okay, so you can see that here is the 10 and the value is 0.693. So I'm going to go ahead and write that here and we're going to round it. So let's say it's 0.7. So we can kind of match it better with what we have here. Make sure you make a note. This is with the calculator and it's based on the model. Okay. For 11, we're going to go ahead and do 11 now. So I'm going to click underneath this one and I'm going to type 11. And there's the next one, 1.47, so about 1.5. Okay, 2012, same thing. We just plug in the next one. So we scroll a little bit down and underneath, okay, we put our 12, which is 3.1461, so 3.1, and so forth with the other ones. Okay, so let me do that real quick. So we have 13, and then we have 14. So 13 is 6.7, 14 is 14.3. So 6.7, 14.3. So you can see that there is a little bit of deviance here. It's not too much of a difference, but there is a little bit of a difference between what we found and then the model. Okay, so it just kind of shows a little bit of a percent error there. Let's look at the next part here. It's saying in what year will the model, so now we're just going to stick with the model because we don't have the data for everything, right? Will the model be approximately $65 billion? Okay, so all we're going to do for this is we're going to plug in that 65 into the S because S represents the money. Okay, so I'm going to go ahead and take my model and go ahead and rewrite it. S equals 0.00036 e to the power of 0.7563 t. You want to make sure you copy everything exactly because it's super easy to make mistakes. And we're just going to plug in that 65. So 65 goes here now instead of my s. So basically we're just solving. And there is a lot of that in this subunit, just so we can get the idea of how to solve using these e's and these bases and all that. So I'm going to go ahead and get the t by itself is what I'm trying to find because I want to know what year, right? So we're going to divide both sides first by 0.00036, and we'll see what that gives us. Okay, so I'm getting 180,556. I'm just going to round, okay? And that's going to be equal to e to all this. Let me move this just a little bit down so you can see what I'm doing. So e to the power of 0.7563t. Okay, and now we're a little bit closer to getting that t. We're going to go ahead and get rid of the e now. To do that, we take the ln of both sides. So I'm going to take ln of this guy and ln of all this. So you can just kind of squeeze it in front. You don't have to take another extra step. And what that does is it gets rid of the ln for me. I'm sorry, the ln e on this side. And I just take the ln of this. Okay. So when I do that, I get 12.1, let's see, 12.1038, okay, approximately. And I'm left with 0.7563 t on this side, okay. Last step, we want to get the t by itself, so we're going to divide both sides by that 0.7563. And so my time is going to be about, we're going to round it. So it came out to about 16 years. Okay. So this means in the year 2016, it would be our answer. Because remember that this relates to the year 2000. And the same thing for this. So my next part is the same question, but for 300 billion. Okay, so I'm just going to set this one up. I'm not going to solve it all completely. It's kind of the same steps, right? So instead of s, we would have our 300. And then we just set that equal to 0.00036 e to the power of 0.7563 t. And we solve. Maybe we'll do this as a warm-up or so this week, okay? But that's the idea for this one, okay? And if you do graph it, and then we did graph it, you can see that this was in fact a growth, exponential growth model. Okay, and this is something I haven't shown you, but all the values that we actually found here can be found here on the graph as well. All right, moving on. Another example. We have 3 more to go. We have the number of bacteria, okay, this is also a growth model, by the way, in a culture is increasing exponentially. Okay, after 1 hour, there's 100 bacteria. After 2 hours, there are 200 bacteria. How many bacteria will there be after 3 hours? Okay, so what we're going to do for this one is we're going to use our model for, let's go back here really quickly so we can see what that model is, for exponential growth, which is going to be this one right here. Y equals a times e to the bx power, where b is greater than 0. Okay, so let's go ahead and write that down. Y equals a times e to the and to the b to the x, b times x power. Okay, and what I'm going to do is I'm going to write what I know and kind of sort of, I don't want to call it a system, but I'm going to have these two equations that I'm going to use to figure out what A and B are. Okay, once I figure out the model that represents this information, I can use it to calculate how much bacteria there's going to be after 3 hours. Okay, so let's go ahead and do that. We're going to have, for the first one, after 1 hour, there are 100 bacteria. And then after 2 hours, there are 200 bacteria. So this tells me that my hours is like the time, right? So usually time is your x. So we're going to say that our hours, I'm just going to put this up here, is going to be our x value. Okay. And the 100 bacteria is basically what happens after. This is how much is left over at the end. So the bacteria is the output. This is going to be our y values. Okay. So for this x, we have this y. And then for this, let's call it x1. And this is y1. For this x2, we have y2 right here. So I'm going to use those two together and these two together. Let's go ahead and try this out here. So for my first equation, I'm going to have after 1 hour, so there's 100 bacteria. So 100 bacteria after 1 hour. So A times E to the B times 1. So remember, my X is my time. Okay. For the second equation, it's going to be 200. A times E, and then B is B times 2. Okay, so all I'm doing is I'm plugging in what I know. The 100 and the 1 go on this first one. The 200 and the 2 go on this one. Okay, and I'm going to work out what I can. It looks like this one is going to be easier to work with because B times 1 is just B, right? So I can get rid of that extra number that way. And what I think I'm going to do is I'm going to try to solve for A, so I can plug that whole thing into the A over here. So we're going to solve for A here. Okay, so to solve for A, well, I have to get rid of this e to the b, right? So I'm going to divide by e to the b, and same thing on this side. And that leaves me with 100 over e to the b power is equal to A. And this is not my answer, but what I'm going to do with it is I'm going to use this to substitute into this guy so that I have everything in terms of one variable and it's easier for me to solve, okay? So we're going to substitute into this guy. So I'm going to have 200 equals, instead of A, okay, I'm going to put something else there. I'm going to plug in all of this right here. Okay, well, not all of it, but this part, what A is equal to. So 100 over e to the power of b. Okay, now here's where a little bit of the rules come into play with exponents and all that other stuff. So let's go ahead and rewrite this. I'm going to have 200 equals 100 times, because you can multiply across, right? This is like saying this over 1, times e to the power of 2b, because b2 is the same as 2b, okay? All over e to the power of b. Okay, so all I did is I multiplied across right here. Now, from there, notice that these two guys have the same base. They both have a base of e, and this one has 2b, this one only has 1. So if you think about it, it's like saying, if you're going with your rules of exponents, okay, it's like you're saying you have 2x and 1x here. So all you would do is you would subtract them, okay? So this part right here is like saying e to the 2b minus e to the b. Sort of, kind of, but we're just looking at the top part. Maybe that's confusing. We'll do division. So all we do is subtract the top parts, 2b minus b. Remember, division means subtraction, okay? So this new part here is going to be 200 equals 100. 2b minus b is 1b, so e to the b. Okay, hopefully that you understood that. If not, you can ask me in class and I can go a little bit more into that. But this is a lot easier to work with now because now all I got to do is get rid of that 100 on both sides. So 200 divided by 100 is 2. And by now, you should know how to get rid of that e. Okay, to get rid of an e, all we do is we do the natural log of both sides. So we do ln of 2 equals ln of e to the b. This is just 1. So b is going to be equal to ln of 2, whatever that is. Let's go ahead and calculate that real quick. Okay, so I'm getting 0.693. Okay, but I'm also going to leave it in terms of the ln because it might be easier just to deal with the ln when I plug back in. So let's just keep both of those in our mind, okay? So we're not done. We've calculated b, okay? So in other words, in our model up here that we had in the way beginning, b is equal to this, ln of 2, okay? I still have to figure out what a is. So what I'm going to do now is I'm going to take what I found. I'm going to use the ln one because I think it'll help me out better. And I'm going to plug it into what I found for a, okay? So a equals 100 over e to the power of b. But b is just ln of 2, okay? So if I keep going with that, I can see here that e and ln are going to give me just that 1 that I wanted, and I'm left with 100 over 2. See, this is why these are both important, okay? And 100 divided by 2 is just 50. Okay, so this means that a equals 50. So now that I have a and b, I can plug them into my equation. So y equals, let me rewrite it first, we can remember. So y was equal to this, right? Where b has to be greater than 0. So I'm just going to plug in my a and my b. Y equals 50 e to the power of ln of 2 times x. And this represents my equation for the bacteria growth, okay? So now the question from the way beginning was how many bacteria after 3 hours? So when x equals 3, what is y? That's what it's asking. So let's plug it in. So y equals 50 times e ln of 2, okay, times 3. And the cool thing is we can just get rid of these guys. Okay, so we have 50 times 2 times 3, which is just going to be 50 times 2 is 100 times 3 is 300. So after 3 hours, there's 300 bacteria. And that is it for this problem. I know some of you might say, oh, well, you could have just gone by, 100, 200, 300. That maybe worked for this case, but it's not always going to work. Okay, so make sure that you still go through the process. Moving on. We have this interesting problem here. This is example number 3, and it's based off of a Gaussian model. So just really quickly, I have a side note here that these models are used to represent populations that are normally distributed. Okay, so normally distributed is kind of a statistics thing. So I'm just going to give you the super quick background for that. It's kind of like, it looks like, and you don't have to copy this if you don't want to. It does something like this. Okay, it has this bell-shaped curve. That's kind of why the graph looked like that, right? Where this area here in the middle, okay, represents the average value of whatever that population, was talking about. So in other words, the maximum is the average value. So if you land anywhere in this area based on this model, you're basically whatever most people are chose or scored or whatever we're talking about. But the farther you land from the model, so let's say you land over here, then you're, either below or above the average, okay? So we're just going to go ahead and we're not going to go too much into that. I'm just going to apply it for this one little example. We have this model, okay, y equals 0.0033 to all that between 200 and 800. And it just says find the average value of this model. Okay, so all we're going to do is we're going to find the maximum value. And we want the y value for that. So I just want to make sure you know how to do that. Okay, so all we're going to do is we're going to graph this, find the max. Let's go ahead and do that real quickly. All right, so here is my model. You're going to see on the graph that it's actually it looks like a line almost. Okay, so I kind of had to play with this a little bit to get what I wanted. This is, since it's super tiny decimals, it's probably going to be very kind of a low maximum, if that makes any sense. So I'm going to stretch out this way. And you can kind of see, I don't know if you see that little like bump looking thing that just popped up. So I'm going, there it is, there's my max. Okay, so now that I know it's somewhere there, I can zoom in. And for this one, I definitely recommend Desmos only because on the other one, it's going to be a little bit hard to see. And there it is. So my maximum value is 511 for the x and 0.0033 for the y. So the maximum value would be at x equals x equals 511, okay? The max is 0.0033, and that's at the y. Really, this is the one that you want. This is the max value, but I'm just showing you where it happens, okay? So again, there it is. Make sure when you type this one out that you do put everything in exactly as it is, okay? Yeah, that's basically it for this one. Okay, easy as that. So average value means you're going to use this. If you have a model like this, it means you're going to find the maximum y value. Moving on to our last example. Okay, we have a logistic growth example this time, and you're going to see it follows the same kind of sort of pattern as the one on the first page. And again, this is summarized here. I did change it just a little bit from the textbook. So it says that UTEP has a population of 5,000 people, and there is this zombie spread infection rate that just happened. Okay, so hopefully it doesn't actually happen. But this rate is modeled by the following. This y equals 5,000 over all this, where t is greater than or equal to 0. Okay, where y is the number of people infected at UTEP after t days. So obviously we can't have negative days, which is why we have it greater than or equal to 0. Okay. The CDC is going to execute Plan X when 40% of the population is infected. So, first question is how many people are infected after 5 days? So, all we have to do is take this 5 and plug it into the time. So, we're going to go ahead and do that. So, for part A, I'm going to take my equation y equals 5,000, 1 plus this huge number 4999 e to the power of negative 0.8. And then instead of t, I'm going to put that 5. And you just plug it in. I'm not going to show the plug-in. By this time, you guys should be pretty good at that. When I plugged it in, I got, give me just a bit, I got about 54. So after 5 days, after 5 days, 50 people, I should say, are infected. And I'm just messing up left and right today. Hopefully these are the slow kind of zombies, like from Walking Dead, not the World War Z, because then that'd be kind of scary. But I mean, either way would be scary. But anyway, besides the point. So after 5 days, 54 people are infected. Okay. Letter B says after how many days will Plan X go into effect? So for this part, we're going to need the second part of the little word problem that I have here. It says that the CDC is going to execute this Plan X when 40% of the population is infected. So the population, according to this problem, is 5,000. So this is the population, okay? And we want to take 40% of that. So we're going to multiply this times 0.40, which is 40%. And that would give us 2,000. Exactly. So 2,000 people is the 40%. Okay. So what we're going to do now is we're going to plug in this 2,000 into the y, because that represents the number of people infected. So we're going to go ahead and do that. So 2,000 equals 5,000 over 1 plus all this e to the power of negative 0.8 t. And in this case, we're looking for t. Okay, so let's go ahead and work this out. This is kind of a fun problem for if you're a math person. But basically what I'm going to do is I'm going to try to get that this part by itself first and then the t by itself. So to do that, I'm going to use this little neat trick first. I kind of want to get rid of that 5,000 first. So what I'm going to do is I'm going to flip everything. I'm going to put that over 1, and I'm going to flip this side. But if I flip this side, I have to flip this side. So my new equation is going to look like the following. 1 over 2,000 equals 1 plus 4, 999, e to the power of negative 0.8 t over 5,000. Okay. And what this does is just visually, it's a little bit easier for me to see, because now I know that to get rid of 5,000, I can multiply both sides by 5,000. And that will get rid of it on this side for me. And I could have just divided it as well, but this just looks a little bit easier to do. So 5,000 divided by 2,000, I believe, is 2.5. Okay, and that gives me equal to all this. So 1 plus 4, 999 e negative 0.8 t. Okay, next step, we're going to subtract 1, which gives me 1.5 is equal to all this. Hopefully you know what to do after this, because from here on it's basically just solving, right? We're going to get rid of that 4999 by division. So divide both sides by 4999. Okay, and this is going to give me just a bit. Okay, so I'm getting 0.0003, 3 zeros approximately, equals e to the power of negative 0.8 t. Okay, and then from here, all I got to do is take the ln of both sides to get rid of that. So ln of this and ln of all this to get rid of that e for me. Okay, so my next step is to take the ln of this. Let me go ahead and do that next. Okay, so I'm getting negative 8.112 equals whatever I have left over here, so negative 0.8 t. And I'm almost done. My last step is to divide both sides by that negative 0.8. So let's do that. Okay, so it looks like my answer is approximately t is equal to, or approximately equal to, 10.14. So after about 10 days, and on the 10th day, okay, is when the CDC is going to have to put this plan into action. Okay, whatever it is. Hopefully it's nothing bad, but this is a zombie apocalypse. So it's probably, chances are super slim. But yeah, that's basically it, guys. So if you have any questions, let me know. A lot of these are just based on the models. Once you can set it up, it's just a matter of solving using the right steps to solve. So let me know if you have any questions.